Okay, so a couple lectures we still have to cover because that's important to understand the parasitic capacitors, digital models. Not too much of content over there, and may spend like 1.2 lecture time. So we'll do it today on Wednesday, and then we cover the circuits of SRAMs, the memory cells. It's because it's so popular right now in the modern CMOS circuits. And then all the lectures for the following 2 weeks will be just directly before the full break, right? Will be cadence tutorials. So it's going to be hands-on. It could be, let me see. We don't have to move to 760. It could be just done over here. This is all based on the desktops. You can log in, remote log into the server, and we can just work in this classroom, right? So you can still come here and you guys work on it. I'll be here. So one lesson that I learned from last semester, because I have clear due dates for the students, and since there were no formal lectures, and students stopped coming to the class, and eventually they won't be able to turn in the assignments because they didn't come, and they feel, oh, there's no lecture anyway, so they want to just do it at home. But actually, they didn't do it at home at all. They just work on something else. So, and 2 students failed from last semester. They did really well for the entire semester, but until the 12th week, they stopped coming to class and didn't submit a lot of cadence, all these lab reports, unfortunately. So please come to class, just like the regular lecture. I may have some ways to control it, like give you quizzes on something, but you probably don't like it. I don't want to waste time on it, since it's already very tight for the rest of the semester. We only have 3 weeks left to work on it. All these so important materials. Okay, so I really don't want to do any lectures anymore. Okay, after this week, it will just totally be cadence, including this week. Tuesday, tomorrow we'll meet in the lab, and I think we'll have to start with Vim. You did Vim embedded.
Yeah.
Anyone else did Vim somewhere else? No? We'll start with Vim first, but we'll definitely set up everything here in the environment. Tutorials. See here, as you can see, if you look at the schedule, okay, this week will be lab 9. It's virtuoso tutorial 1 to 3. So what you are going to expect is these the cadence virtuoso tutorials 1 to 3. Okay, I think until the third one, you are getting to the point to build an inverter in the cadence environment. Okay, and then 4, 5, 6 will be lab 10, 4 to 7, and there will be one that I will post to Dropbox, since I cannot publish it on my website. So Dropbox, and you guys will have access to that Dropbox folder. And then the third week, you'll go through the RTL to GDS to workflow. And we are not going to have any assignments from the lecture, right? So it'll be totally just hands-on labs. So it makes sense that there will be a little bit more workload over there, since I won't have any like quizzes or assignments from the lectures. It's basically just labs, right? So please do spend time on it. Okay? Oh, we'll merge these two. Probably we'll merge these two to one, since we don't have 3 weeks instead of 4 weeks. All right. Let's get into the topic today. So building these, understand all the time delay in digital circuits. So the starting point is a Miller effect. It's called Miller effect. It's all because the transistor is being shorted to VDD. So whenever you are, like this one, right? Like this one. If you pre-charge this to VDD, so it's a floating VDD, and you have a pulse being given to the gate, So this will be discharged from VDD to ground, right? So you give a 1 pulse, and this one responds that with a VDD to 0 change. So eventually, if you consider the overall voltage change, it's changing by 2 VDDs. It's changing by 2 VDDs for this capacitor. If you model this circuit in something like this, one cap in the middle and 2 voltage sources, right? If you give a 1 VDD pulse, and this is pulling down to 0, from VDD to 0. So in theory, it's a bit weird, but in theory, the total voltage change is 2 VDD for the cap, for the capacitor in the middle. So the reason I'm putting a capacitor over here is because, the NMOS transistor has the gate and the channel, right? So it's forming a little capacitance. Same to the other half, right? If you look from the cross-sectional view here, so we modeled it with two halves. So the entire capacitance over here is COX, we call it COX, oxidized capacitance for the gate, right? So COX. So for each half will be a half COX. So I have 2 half COX over here. And for this one, we modeled it, two capacitors, and each one the value with a half COX. Okay, if we model it this way, from the top, the top part of it, right? Input output. There's a little capacitor in the middle. So it's basically changing. This is changing from 0 to VDD, and this is changing from VDD to 0. Okay. You can consider this is a voltage gain at like a -1. Is it -1? This is plus VDD. You're getting minus VDD change. So it's -1, right? So it's -1 gain, voltage gain. So if there's a voltage gain, even though it's a negative gain, if there's a voltage gain for a circuit, and the input capacitance being seen by the source or by the whatever signal over here will be increased. That's called a mirror effect. So if there's a voltage gain of the circuit and the input capacitance being seen by the source or by the driving signal will be increased. So the reason for that is if you look at the voltage change to the cap, it's actually getting 2 VDD, delta V, for the cap. So the overall voltage change is 2 VDD. So in that case, the overall Q becomes 2 VDD minus just one, Q will be VC, right? So it's going to be 2 VDD minus the capacitance, because Q, the charge, equals to VC, right? Okay, that's from physics. Okay, charges equals Queen is Victor times Charlie. So Queen, Q, the charges is V times C. Okay? And so the effective delta, C effect, so the effective capacitance seen by the driving source becomes delta Q divided by VDD, because the driving source is only changing by 1 VDD, right? So being seen by this guy is only changing 1 VDD. So delta Q divided by it is 2 VDD times C over VDD, right? So the effective capacitance seen by the source, the driving source, becomes 2C. That's why it's saying that what is a mirror effect is all because the driving source is seeing a larger than usual input capacitance. So it's increasing the load, right? So in that case, because of that, we could remodel this circuit into this. So we separate that little capacitor into 2, because the input is going to see a 2C here, and output is also going to see a 2C here as well. It's just one being split into two C's. So every source is seeing a 2C on at their end. All right, that's the theory behind the scene. We don't have to dig too much into it, and they build a model to analyze why it becomes a larger input resistance capacitance. It's same to the output as well, because it's just the same voltage change. So it's going to be 2C here, 2C here, and we know the conclusion here, and which is applied to our circuit design. And eventually, all these results can be verified by testing with the old equipment in the lab. It shows you the larger input and output capacitance over there, and this is why. This is how this is getting explained, right? That's called Miller effect. So we are going to use this theory for our CMOS transistor modeling. For example, the NMOS transistor model becomes as follows. Right, you have an NMOS transistor, like this, and we modeled it in this way. Here's the input, here's the channel resistance, and the switch. We got two capacitors. So this guy has a capacitance, stores the charge at the very beginning. It's a load capacitor, CL. Channel resistance Rn. So now let's see, what are these capacitors? What are the values of these two capacitors? So this one has one capacitor on the top, and this one has a capacitor at the bottom. And you can see that this is grounded. This is 0 volts. There's 0 volts. So whenever this one have a rising edge, from 0 to VDD, the channel will be opened, and whatever charges pre-stored, for example, it's a VDD pre-stored at the cap on the cap, will be discharged. All right. So if this one from 0 to VDD, and this will drop from VDD to 0. So we can easily tell that this capacitor here has a Miller effect. All right. What about this one? It doesn't, because it's tied to ground. So if you change this one, have a jump at the gate, this is not going to change. The voltage won't change, even though there's a current flow into it, but there's no voltage change. So this capacitor doesn't have any Miller effect. So we model it in a digital model, right? When you are analyzing the parasitic capacitance of the circuits, we actually consider, when I draw it like this, physically, each half is basically a half of Cox or Cox, right? Each one. Because this guy has a Miller effect, so this becomes what? Like two. So this, you split this guy, it becomes, if you look at this one, right? So you can split that capacitor over here into two capacitors and double the value for each side. So it becomes COX for each, right? So this will be COX, and this one has grounded COX as well. And what is this? This is a half COX. So for the total input capacitance into the gate is how much? 3/2, right? So this is 3/2 of COX. You add these two. And for here, you'll have a COX over here in parallel with your load capacitor, whatever the load is, right? You're having COX and the load capacitor in parallel, like this. So this is our NMOS model for time delay for the digital design. Okay. Any question on this? And there will be a, for example, we have an inverter. You have PMOS and NMOS in there, but just for example, we are looking at the inverter. And here's the input, output. So there will be a time delay, like this. Okay. So for the inverter circuit, it's like this. Here's the output. If the input is going up, NMOS will be involved or be engaged because it's discharging it, right? PMOS will be off. So in that case, this model will play a role in here, and it's causing a time delay. A time delay whenever this is pulling up, the gate is getting put up. If this is pulling it down, this will be shut off, and this will be on, right? It will be on. So it's getting put up to VDD. So the RNCs in the PMOS model will be engaged instead of the NMOS, right? So the PMOS's voltage model looks like as follows. PMOS model is a bit different. So it looks like this. Here's a gate and VDD, channel resistor, switch, RP. So we know that the PMOS looks like this. It's VDD, right? And there will be 1, 2. So which capacitor has a? So what's going on is whenever this is pulling down to ground, and it turns on this PMOS and start dumping charges to this cap. So this is your load capacitor, actually. It's a load capacitor, right? So which one has a mirror effect?
The one next to the load capacitor.
Yeah. So this one's a mirror effect, right? And that one very similar to the NMOS theory over here, right? So the input capacitance consider half of one over here, right? So this is half, but eventually the mirror effect, because the mirror effect, this becomes COX. And this doesn't change on the other side, it's still VD. So this one doesn't have a mirror effect, it's just half COX. So the input capacitance for the PMOS is also 3/2 of COX. And we'll split this one into 2 parts, and each of them is a COX. So the one being in parallel with the load capacitance is also COX. That's a PMOS model. Okay. So when it's causing a time delay like this for the inverter, depending on it's a rising edge or falling edge, we analyze the output accordingly. So we'll look into that, why we are looking at the output. So whenever this one goes up, for example, it goes up. So this is being engaged because this is turning on, getting turned on. It's discharged whatever has the output to the ground, right? So we have to use this resistor for to calculate the time delay. Okay, because the current is not going through the PMOS RP, it's going down. So it's going to be this resistor instead of the PMOS resistor, like this. All right. So there are a couple of different parameters. So if you look at the input, 50% and 50% of the output, you get this period, and that is called, you are always looking at the output. So that is called TP, it's a time delay, PHL. So the reason it's called PHL, not LH, is high to low of the output. So always looking at the output, not the input, for the propagation time delay. So this is called propagate delay. It's input 50% to output 50%. It's called TPHL because its output is from H to L. And there's another parameter you may see somewhere else. It's called TF or TR. So if you are taking 10%, 90% and 10% like this, that's a 90% of the voltage. So this is 50%, right? 50% of the voltage. And for T, this is T full, right? T full. It's falling. It's falling. It's from 90% to 10% of the voltage range. That's called T full. So this one, if you also label the 10% to 90% this time, that's called T rise, TR. Yeah, obviously, if you label 50% here and 50% here, so what is this should be called? T what? Input output and 50%. TP LH, right? So now let's look at the calculations for that. Right? I can skip this one probably. Should I? Let's do this one still. Let's look at one example here real quick. So I think it's here's a table. It's from the textbook. Okay, example. On page 320. So it shows you the NMOS parameters and PMOS parameters. Size is 10 micron over 1 micron, so width over length. 30 micron over 1 micron, so width over length. And for R, N, or P, depending on its NMOS or PMOS, and that is 1.5 k ohms, 1.5 k ohms. And COX, N, or P, depending on the NMOS or PMOS, is 17.5 femtofarads. So get a concept of the capacitance level of all these COX, right? 17.5 femtofarads, like that. And it's asking you that what is the TP what, right? If you have a circuit like this, giving a pulse, TP what equals what?
TP pole is equal to HEP power is equal to some.
So TP what? TP.
TP AL. TP pole or TP pole.
So initially it stores the VDD, and when you pull this up, the output will do what? Will be discharged, right?
Yeah.
So it's actually from high to low or low to high. High to low, right?
Yeah.
And that equals what? Depending on the size of the transistor. The size of it is actually 10 micron over 2 micron. The size is not given in the table. The size given is 10 micron over 1 micron, right? So what we need to know for the TPHL, so we need to know the 0.7 Rn, and the low capacitance is 50 femtofarads, CL. So we need a what? If you look at the model, it's like the output over here. It should be Rn times the addition of these two capacitors, right? Okay. So 0.7 Rc. So C is the COX plus
CL.
CL, right? Okay. So we don't know this, we don't know this. What are they?
And then
What is RN?
1.5 ohms.
It's different sizes.
Oh, yeah.
So the bottom one is what? The denominator is what? Length or width?
And it's long.
It's length.
Yeah.
Okay, so it's longer or shorter?
It's shorter. Or is the table shorter than?
Yeah, so this is longer, right? So the actual one is longer. So 2 times longer, right? 2 times longer. So 2 times longer will give you a smaller resistance or larger resistance? Larger resistance, right? So the resistance will be
2 times that?
3K, right? What about the capacitance?
The capacitance would increase, or COX would increase.
Increase by how much?
That'd
It
be,
will be 2 times of this one, right? Because what is larger? Because what is larger?
the length. So
C equals what? Epsilon A over T, right?
yeah,
So T is
thickness. Or
can we change it? No. It's depending on the process, right? So the foundry will do it. That's the thickness of the layer, how long they do the deposition of the nanomaterials,
yeah.
semiconductor materials, right? So you can actually control that. But A will be changed because the length is double. The length is double, so which means the area will be doubled, right?
Yeah.
And your C will be doubled. So basically you're getting 35 femtofarads.
Yeah.
Okay. Plus
50.
50 femtofarads.
85 times 7.
Okay, so you can do the calculation. So what if I have a capacitance over here as 1 nanofarads? What's gonna happen?
It's gonna,
Oh, 1 pico. 1 nano is too much. That's crazy. 1 pico.
it's still explode at time delay, isn't it?
Yeah. So you could ignore this guy because this is like
Trivial.
200 times. Yeah, it's gonna be trivial, right? So you can directly ignore that in the calculation. So that's for this example for a single transistor. But also if you look at the inverters. Inverters. So inverter like this. So it'll be 1, 2, 3, 4. So input comes in, and because it's getting insulated by the gate from the input to the output, but I still want to model the capacitance. So for the NMOS, whenever it's going up, it goes up to VDD for that side. You're having the NMOS input capacitance, which is 3/2 of Cox N, and this will be 3/2 of Cox P. As the input, and it's being insulated from, not really insulated, but it's been getting separated from the output because of the gate, right? So we want to model the gate this way. The channel still goes on, but the channel directly shorts to the output, so that's a legit way to do it. So this will be RN, this will be RP. And because the output is also shorted to all these capacitors, because when you separate this one into two, you split this one into two mirror effect capacitors, and you are getting two Cox, right? Cox N here and Cox N and the output as well. So basically you draw a Cox N here, Cox P here. No, P on the top, and then at the bottom. Okay, bottom Rn is top Rps, right? That's one inverter. That's one inverter. So if you have two transistors in an inverter compared to the just single single transistor analysis like this one, and TPHL will be 0.7 R because HL is high to low. It's going through the Rn, will be Rn still. However, the capacitance will be different. Since this node is also shorted to the PMOS COXP as well at the output. So this becomes COX P plus COX N HL, high to low, yeah. And for TPLH, this becomes 0.7 RP. It's pulling up times the same capacitor. Same parasitics. Because that's the same node. Doesn't matter if it's being put up or put down. So they all experience the same effects of the two capacitors over here, like this. You are saying, hey, this is shorted to the VD, this is shorted ground. This should be different, right? But actually it's not. For like a transition like this is considered as an AC signal. I don't know if Dr. Jetson covered that in analog or not, but for AC signal, VDD is the AC ground. Did he mention that? So DC sources are AC grounds.
Yes.
Why? Because there's no AC signal.
Yeah.
That's it. It's a bit confusing. I mean, it confused me for many years when I was a student, but it's actually really simple. Why it's a AC ground? It's because it has a zero. Ideally, it has a zero resistance, right? Has a zero. So all these ideal DC sources, they have a zero resistance, and so it's voltage on one side and ground on the other side. So if AC signal goes through it, there won't be any drops. It's directly being shorted to ground. So there's no AC can happen in the DC source. So that's why it's considered as an AC ground. It's confusing, but we just accept it, right? Just accept it. So if you model it, actually, when you are doing the AC analysis, you always ground this pin. So it's basically like you are twisting this one to ground. So you have two caps shorted to ground if you do AC analysis. So they're equivalent. Doesn't matter it's pulling up or pulling down. They both contribute to the time delay because they're equivalent for any of these AC signals. Okay. So these are the time delay for that. And what is the total C in? Input capacitance. What is the total C in?
It would just be 3 mouse times 0 plus 0.
All right. I think that's everything we should know about this guy. And then the next one is if we form a circuit using the inverter, like the ring oscillator we learned. Looking at this node. So this node involves both output and input, right? So if you start from here and ends here, it looks like this. Input goes up, the input capacitance, and here and then the output capacitance. That's one inverter, and the output goes to the input of the next one. And then here's a gate. Here's the output. So that's the digital model of it. So now let's label the capacitance of this circuit. So this one is 3/2 of CUXP. This is 3/2 of CUXN. This is RP, so RN. This is CUXP, CUXN. This is 3/2 of CUXP, 3/2 of CUXN, RP, RN, CUXP, CUXN. Okay. So for this node, we're looking into the time delay for this node. What are the capacitors and resistors are getting involved in here?
We have to add the CN at the next step too, don't you?
Yeah.
So it would be COX P plus COX N.
So it'll be
Oh, CX.
5/2 of CUXP,
Yeah.
right? 5/2 and also 5/2 of CUXN added together. That will be a total C. Since you're adding these together. Okay. And which resistor is involved in here? Are these involved?
No.
No, because there's a gate, right?
Yeah.
These are involved. So when they are looking at the output, I want to have you guys have a very brief model in your mind. You can imagine. So the one before it, that inverter's channel resistance are getting involved, but not the one follows it, right? Because this has a direct connection to the channel, but this one doesn't. Okay, because there's a gate in here. So when you're doing the calculation, you need to pay attention to the RP and RN of the previous one, not the one follows it. So in the case that you have different RP and RNs, different sizes of the transistor of the inverters. So for this one, you have 0.7 R. If we're doing TP LH, pulling up, right? Pulling up. So that's going to be RP, right? RP times this. For TPHL, it's going to be 0.7 RN times this. Any questions by far? No? The ring oscillator we built in the lab, why it oscillates? Did you ask you that question? Why it oscillates? That sounds crazy, right? Why it oscillates?
It's because of the time delay, right?
Yeah, time delay, because all these propagate time delays. Okay, so if we have this guy, if this one, at the moment, there's a pulse, and after a propagate time delay, it will do this, right? Oh, so this, we'll do this here, we'll do this here, we'll do this here, we'll do this here, and we'll do this here. And you're like, hey, the same wire, this is pulling up, this is pulling down. Is that possible?
No. Well, if they happen instantaneously, no. But if there's a time lag, then maybe.
Hmm? What's happening? These are inverters. It should work. It should inverse it. These are powered, right? They're powered up and grounded. It should work. If there, at the moment this wire has a pull up, and then you do this. Oops. What's happening? Why does it have different voltages? Could that be possible? They're the same node, yes, but this pulse is a voltage at the same node, but several nanoseconds after. It's still itself, but at a different time points. All right. So what's gonna happen? So if you do this, have an odd number. Remember, has to be an odd number. If it's an even number, you are seeing these two. It's basically just a time delay, right? Just like this. But not oscillating. If you are doing this, it's going up, and after a few nanoseconds goes down. So it starts oscillating. That's why it's a ring oscillator, because it starts oscillating. So if you probe here, you got an oscillation. You probe here, what you are going to get.
Just delay. What's the time delay?
I draw it this way. What if I draw this one on the top and move everything over here? Right? So this make this one looks like the last one, and then what's the difference? All the inverters in the ring oscillator, they are equivalent, right? So all the time delays. If you probe here, you got oscillation. Probe here, you should get the same oscillation, but with a time shift, with the phase differences on phase. They're equivalent, right? It's a different way to draw it.
Yeah.
It should all the points should be oscillations
Yeah.
with same pulses but different phases, right? So see here, from here to here, if you look at this point, I'm getting what? 1 watt, TP what?
Low.
Yeah? Right here.
A little high. Yeah.
1, 2, 3, 4, 5, right? Four. So this will give you what? Give you this. Okay? Connected. It's a pulse. Right? Then it will be invert again, and it will do this. Oh. You agree with that? See here?
Yeah.
We just did this, right? We did this, and we know this will happen as well. You agree with that? Okay. So, for this one, for this simple process over here, we're getting 1 pulse. Is that 1 period? This is 1 period. This is 1 period. Is the pulse a period?
Yes.
No, it's half period. You need a 1/2 to be on and a 1/2 to be off to form 1 period. So this guy is half period. So if you add all these delays together, it's going to be half period. So we only analyzed the pulse. What about the dip? The dip, you are having TPLH plus TPHL plus TPLH plus TPHL plus TPLH. So how many TPHLs and how many TPLHs for 1 period? 5 TPHL plus TPLH will be 1 period. So what's the oscillation? What's the frequency of this oscillation? Since when you design a ring oscillator, you are actually creating a clock signal on the chip. That's the easiest way to create a super high speed clock. It's a lot of times being used for high speed cameras. So for the shutter of the CMOS camera, usually the crystal clocks externally cannot give you that high speed clock. So for on-chip high-speed clocks, you could easily use an odd number of reverters to create a super fast clock. So the reason for that is if you get into the parameters, if you're plugging the numbers, especially when you are using a really modern CMOS process, and these are only like several femtofarads. If you plug in, you are creating like probably sub-nanosecond time delays. And it's easily you can get gigahertz of oscillations. And so the modern CPUs are running that fast, right? Several gigahertz, right? Several gigahertz. It's crazy. Like billion times the oscillation in 1 second.
It's like a little fast.
So this one over this will be what?
Frequency.
Yeah, that's oscillation. So you have there might be a question, I'm trying to reduce the number of homework assignments, but maybe there will be a quiz on it, right? I'll ask you, for example, I need a frequency to be 5 nanoseconds, right? No, 5 or 500 megahertz, okay? Or faster. So I let you guys design the ring oscillator for me to make it happen, right? So maybe the size, depending on the sizes of the transistors you are getting, eventually you are find out, hey, maybe 11 will be enough, right? But to reach this frequency, you might need to have to change. For example, if for calculation you calculated like 11.2 inverters, right? It's needed. So this will be n, right? This will be n times n, right? So this is given, right? And ask you guys to calculate for n, right? So how many inverters are needed for this? If you do the calculation, you'll find out it's 11.2, right? So in that case, how many inverters should you use? If I need a frequency larger than that. That's the number you got, right? So how many inverters, how many stages of the inverters do you need for the ring oscillator? If this is a calculation, after calculation, I find out this number, for example, for n, right? Yeah, how many do you need actually? 12 or 11? Huh? If you have more,
11.
yeah, if you have more, is it giving you more delays or less delays? Definitely more, because more stages will give you more delays.
Yeah.
So the fastest one is probably 5. I don't know why people usually don't use 3. There might be a reason for that, but usually 5, is the smallest number. If you find out this, it's not 5 yet, right? So it's not like 3 or 5. So you can easily pick up. It should be 11, because 11 is smaller than this number will give you a faster clock than this one. Okay. You could tell the quiz will be on Wednesday. Fortunately, right? Any question on this? One more little thing here to cover. I'm so ready for it. Just do it, Dr. Lee. Running out of time. I'm sorry. I'm disorganized. This is really simple, just one simple equation, okay? Can do it really quick. So for the inverter, when we model the dynamic power dissipation, don't have to dig too much into it compared to circuit 1. We analyze the AC power, reactive power. All these kind of different power sources. But this is just super simple. We just consider the average power being consumed by the circuit. And it's just a way to quantify the power consumption, but it won't be exactly the power consumption for the circuit, right? So because there's a load, right? So for the EDA tools like Cadence or other things, they can extract the parameters and do analysis and eventually tell you what the parasitic capacitance is for all the following circuits that this inverter need to drive. But now we just model everything as a CL, right? As a low capacitance. So the average current going into and out of, we consider all the currents, but the average current in all these oscillations could be modeled as the total charges divided by the period of the digital signal. Okay, so for on it charges, for off it discharges. So both processes have the charges going in or out So that consumes current for both processes actually. So that's why we use a whole period for the time. And that's the total charges getting involved in that event. And we all know that this equals VDD times the total capacitance. The total capacitance including the load capacitors and whatever involved at the output of the inverter, right? So these are all the capacitors involved. So let's call it T total, and divided by T, right? So P average equals I average, which is the one we just calculated here, times VDD as a power supply. So VI is P, right? And this, eventually this becomes VDD square times C total over T, and this is frequency because 1 over T is frequency, so this eventually becomes VDD square times C total times F. Okay, so this brings up a really important concept over here. This guys, all the modern IC design, right? So when we have a chip, we want a less power consumption, okay? So we want to reduce the frequency or not? No, we want CPUs to run at a faster rate so you can do a lot of jobs. So this is not a good idea. So I have to increase the frequency, and I can tell from the products, the commercial products, they are actually, the frequency is increasing over years, right? So higher frequency will give you what? Higher power consumption, definitely, right? So what you can do, what else you can do? The capacitance, drop the voltage, drop the capacitance, okay? Yes, smaller devices will give you smaller COX. And smaller devices will require less threshold voltage and lower VDD. So the C5, we are doing 5 volts all the time. But for 180, when you guys are doing the cadence, you can find out, oh, a lot of devices can just handle 0.3 volts easily. And actually for the CPU, for the core, even 180, we can use 1 volt as VDD. Just 1 volt, right? So we reduce the VDD dramatically, and it's getting squared. So you can see it's like 25 times less over here. Also, small devices will give you smaller C total, but you are having like billions of more transistors in there, but actually the total capacitance is probably not changing too much. You can control that because you just want more things to be integrated into that chip. So the thing is, you want to increase this one, decrease VD, right? That's the overall conclusion that guides our modern IC design in the industry. Okay. So there will be another lecture. So I think we're done. So we're doing this faster. So on Wednesday, we'll run some SRAM circuits and do our quiz. And after that, we'll just let you guys work on cadence. All right. See you guys tomorrow in the lab. So.
Will Wednesday's quiz be on the SAR block or this?
SAR block.
Okay.